we want to move towards being able to solve these equations, namely, in this class, momentum and mass and momentum, right? And so what are we solving for? So let's just, I'm going to write down this. It'll be a little bit explicit, but recall conservation of momentum. We derived it last time. Where here I've utilized the fact that the Cauchy stress through angular momentum is symmetric. Prove that. Right? And also I'm going to use the identity that the time derivative of u is equal to v, right? So when I write down, now I'm going to write out, so remember this is a vector equation, so it actually represents multiple equations. And I'll just, to be explicit, I'm going to write them out. So here we have three equations. So, what we're solving for, what we really care about is we want to know the motion of the body, right? So the u's, right, the displacements. And so we have three equations, but how many unknowns do we have? Because we define stress, but only geometrically, right? Only through this sort of octahedral thing, which just gives a geometrical or representation between the traction forces and what a normal vector in the stress is, right? But not any relation to the displacements, okay? So, we have the three displacement unknowns. And you might say we have the 9 components of stress, but the stress is actually symmetric, right? So it's really just 6 components. So we have the 6 components of stress plus the 3 displacements. So we have 9 unknowns. So we can't solve this yet, right?
Should it be d squared?
Yes. Thank you. So what else do we know? What other relationships do we have with displacement? And what we really want is we want everything back. If we can write those equations all in terms of displacements, then we could solve them, right? So what else do we know? We have, do what? We do have energy, and we'll use that in a second. But, something that we have the kinematics that the first thing we talked about is, we define the strain, right? So the strain we define in terms of displacements. So remember we And here I'm talking about the small strain. All right, and again, just to be explicit, right? So there's 6 more equations that have displacements in them. So if we could just figure out a way to connect the strains to the stresses, we could solve our momentum equation, right? So that's what we need. It's called a constitutive model, right? And it's basically a relationship between stress tensor and the strain tensor. And if we can come up with that or propose one, because quite frankly, a lot of times constitutive models are just proposed, right? They're just based phenomenologically on observations from experiments, right? We're going to try to do something a little more rigorous. Based, we're going to make thermodynamic arguments to try to come up with it. But this is what we're chasing, right? Because if we can get this, then we can solve our momentum equation. We have enough equations to solve it. So we're going to make a thermodynamic argument. So let's assume a thermodynamic equation of state. Of the form U, where U is the internal energy per unit mass, where U is a function of the entropy, a yet unspecified, possibly vector-valued number of internal state variables. And at least this first time I'm going to say position X, but I only mean position X in the sense that a body made up a bunch of points X, right, could be heterogeneous. So the internal energy could be different at different points, and that's why it's through its dependence upon X. But otherwise, there's no spatial dependence in the sense of like a kinematic dependence. So if we just know S and the internal state variables, we should be able to determine the internal energy, okay? And I don't know who wrote it on the board, but there's an example of a very simple, that wasn't me, but that's an example of a very simple equation of state, right? The ideal gas model. So, if we know any two of the unknowns in that equation, like pressure and temperature, we can compute the volume, right? Or if we know pressure and volume, we can compute the temperature. Okay, so I'm just going to rewrite this, dropping the dependence on X, because again, that's just to say that the body could be heterogeneous. So then we're going to define the thermodynamic temperature as the change in U with respect to a change in entropy with constant internal state variables. So that's what I mean by this notation. So if I hold the internal state variables constant, then this is the temperature. And I'm going to introduce something new called a thermodynamic tension, which is a vector. That's the change in internal energy with respect to the internal state variables at constant entropy. Okay. So for a change in U, I mean this guy, if we just apply the chain rule, du ds plus du that's equal to, if we use our definitions, this guy. This thing is called Gibbs relation. Has anybody ever seen that before? So actually when Gibbs presented it, he presented it only for a fluid with a single internal state variable. That's the specific volume. So then you'd have something like where minus P is du dV, yes. So this minus P, that's the thermodynamic pressure. Okay, so I just wrote that because this may be a more familiar way that you've seen this equation. This is a generalization. Yes, sir. What is? I'm sorry. Oh, it's called a thermodynamic tension, but don't worry about what it is yet. It's just sort of the energy conjugate to the internal state variables that I haven't. Remember, I said they're arbitrary, or I didn't say they're arbitrary. They're yet undefined. We haven't chosen them yet. Okay, so they're just. This is just a conjugate variable, meaning that this adds up to internal energy, right? So it's just sort of a placeholder. And then once we choose what these are, then this will have a physical meaning. I'll come to that. It's a good question, though. Okay, so for a given x, we have that the temperature can be a function of entropy in the internal state, and the tension can be a function of the entropy in the internal states. And we're going to assume that these relationships are invertible. That is, we could, if we had a functional form of this equation, it's invertible such that we could solve for s in terms of t, right? So we could solve like this. And so then if we substitute, remember our internal state equation was something like this. Right, so we want to substitute this in. So now if we replace s in this equation, now we have a function of t, right? So like that. And likewise for this equation, right? If we plug that in, then we have and if this is invertible, we have this. All right, so the idea here is that I just want to say that basically any of these internal states can be a function of the other ones, right? I mean, it's sort of just like that equation, like the ideal gas equation. And with that, we'll introduce the concept of a thermodynamic potential. With that in mind. And the one we're going to use, there's actually multiple choices, but the one we'll use is something called the Helmholtz free energy. And we're going to use the symbol phi for that, and it's a function u minus st. All right? So this is the energy or I'm sorry, the amount. This represents the amount of obtained or stored energy in a closed system. At constant T. So through the inversion relationships, we could actually choose to specify this using any independent variables we want. But if we choose the temperature and the internal state variables to be independent quantities, then we can show that a change in that free energy can take this form. And if we divide this equation by dt, where t is time, and I'm going to now switch to my notation because I don't want to have d big T over d little t, right? So I'm going to use a dot for time derivative, okay? So we have this. Are we okay with that? So I just divided the first equation by dt, but then just switched the notation, where the dot means time derivative, okay? But if you remember, the assumption of the Helmholtz free energy was at constant temperature. So there's no change in temperature. Yes? Do. Oh, sorry. Thank you. So the assumption of the Helmholtz free energy is that it's at constant temperature, and so that term goes away, and so then we just have that this. Okay, and I'm going to call this equation star because, or call it equation 1 or whatever, because we're going to come back to it in just a second. So sort of holding the Helmholtz free energy in our pocket, let's remember the energy equation that we derived last time. And from the Helmholtz free energy, we have this, which implies this. So if we plug this in here and just work through the details, and I'm also going to, here I'm going to use the dot notation again. But again, our assumption is constant temperature, so that term goes away. And then we're going to return to the Clausius-Duhem inequality, and we're going to assume that the process is reversible. So a reversible process is an idealization, but that would be the only time when the left and right-hand side of the Clausius-Duhem inequality would actually be equal to one another. Okay? So if we do that, then we have this. And if we plug that in here, then the whole equation, this whole equation reduces just to this. And of course, in the case of small strains, we showed before that this is a good approximation. And so, yes?
Explain this last equation.
I think you missed it. You got here late. You can go to watch the video. It was the very first thing we talked about. It's the second law of thermodynamics, basically. This is truly this is, it looks like this, but if we assume the process in it is reversible, then it's that. Okay. But yeah, you can go back and watch the video. So if you then basically comparing star, star, and star, then you can see that, well, let's just write up here. you can kind of see there, so that this gets back to the question, you can kind of see that if the choice of internal state variables is the strains, then the thermodynamic tensions are the stresses. And this is a very weak or heuristic argument I'm making here. You can actually do it very formally. And if this was a continuum mechanics class, I would do it. But you have to introduce some different stress measures, actually. There's other stress measures than the Cauchy stress, like the first and second Peele or Kirchhoff stresses. And to make the really rigorous formal argument, you have to introduce those concepts. And as we move forward in this class, because we're assuming small strains, we will never need those stresses. And so I just want to avoid kind of additional work there, or development. Okay, so this is a very heuristic argument, but you can see there that if the internal state variables are chosen to be the strains, then it's sort of analogous that the tensions are the stresses.
Professor,
Yeah.
I have a question that how did the material time derivative change to the dot thing?
Yeah, it's a little bit of an abuse of if it's a little bit of an abuse of notation, but it works out if you'll just trust me, because if you want to see the details, I can show you, but let's just move forward if you'll trust me. Yeah, it's abusive notation, but yeah. Because I really want to get to the point of all this. So if we have this equation, oops. We have this equation. So if we take the derivative with respect to sigma ij of both sides of this equation, sigma ij dot. Epsilon ij dot, sorry. This is just del ij, so we finally have, and there's also a cancellation of dots identity, but in the end, what we have is this. So we have that the stress is a function of the partial derivative of the Helmholtz free energy with respect to the strain. And so you might call this guy W. It's just the density times that. And this is a strain energy density. Well, I'm sorry. If we define W to be rho times the Helmholtz free energy, we call this a strain energy density function. And so with that, we have that the stress is a function of, or the partial derivative of the strain energy density function, which is a scalar function of the strains so we have this relationship. So and with that, we can, if we take the time derivative on both sides of the equation, because this is a function of the strains, and that's a function of the strains through that heuristic argument I made, that the Helmholtz-free energy, the internal state variables in the Helmholtz-free energy are the strains, okay? And, it's a lot of math, but, I think everybody sort of intuitively knows this, what the Helmholtz-free energy is, or the strain energy is. If you've ever played with a rubber band, right, you pull on the rubber band, and that resistance, that internal resistance to strain is the stored energy in the rubber band, right? That's sort of the free energy in the rubber band. So if we take the time derivative of both sides of the equation here, we end up with a rate form of a constitutive equation. Through the chain rule. Okay, maybe I should say KL. All right. And so this is a constitutive equation. You may not like it because it's in rate form, but it is a constitutive equation, right? So it's a relationship between stress and strain, or stress rate and strain rate, okay? And a lot of times what we do is we call this guy an elasticity tensor, and it has components I, J, K, L. Okay? So that's a fourth order tensor. And because I, J, K, and L all go from 1 to 3 at maximum, in 3 dimensions, then it has dimensions 3 by 3 by 3 by 3, or it has 81 components. And the more common way to see this written is, this will be true to within a constant of integration of this relationship. Right? And since we haven't defined what the CIJKL are, we could just fold the constant of integration into them. So this is our constitutive relationship. It's also otherwise known as generalized Hooke's law. So everybody's familiar with Hooke's law, right, from all the way back to physics, right? So typically that's just one dimension. So Robert Hooke was like an experimentalist, I think Love actually developed this for the first time, this constitutive theory, but yeah. So we have our constitutive relationship, but it has 81 constants. Dang. That means we have to go to the lab and we have to do 81 independent experiments to populate that thing, to be able to use it, right? Well, maybe not. We know that sigma ij is symmetric, right? So that means that this is also true. That's called major symmetry. And that reduces our 81 to 54. That's better. We also know that by definition, the strain is symmetric, right? So that means that this is true. So that takes our 54 to, oh, what is it, 31? 36, couldn't remember. To 36. And we also remember that the way we derive CIJKL is from that strain energy potential, which is this. And because the order of differentiation doesn't matter, right? If I had a strain energy potential, I could differentiate by epsilon KL and then differentiate by epsilon IJ, and I'd get the same answer as if I differentiated by epsilon IJ and KL, right? That doesn't matter. So that implies that Cij KL is equal to CKL IJ. And that takes us from 36 to 21. And without any other planes of symmetry, that's it. If you have a truly anisotropic material without a single plane of symmetry, you'd have to do 21 experiments to populate the constituent model. But thankfully, it's very rare that that we encounter constituent models like that, or real materials like that. Almost real materials, all real materials have at least one plane of symmetry, and that can reduce it much further. And that's what we'll do next time. It takes a little bit longer arguments to do that, and I didn't know if we'd have time for it today.